So we know what simple means. It means that the algebra, the superalgebra G has no non-trivial ideals, and it is non-abelian. And we've seen a criterion in the book of Mousson. This criterion should help us to determine whether the superalgebra is simple or not. So the criteria we saw, so is, where is Marta? Because I thought someone is missing.
Are you sure this is free?
It's not free.
So
But the other one, it's not free either. So we stay here until they kick us out, and then we hope going to the other that there is, but we don't know.
Yes, actually I was, because I saw there was no free room, and so I was calling you. I was calling everybody.
It is a sad thing. I'm disorganized. So I was thinking about Marta because she made an observation about this criterion that is correct. You remember this criterion was that if we take an idea which is non-zero, and it is a G0 submodule of G1 of the algebra, then we have that G1A is contained in A, then implies that G1A is equal to G0. Let's write it and make the comment later. And then we have G1 is faithful as a G0 module. And 3, G0, G1 is equal to G1. Now, this condition, see, so if we have that G0, G1 is equal, right? Yeah. So what was it, Martha? I forgot. So this is a condition that is always empty, right? It cannot exist an ideal doing this. Because, right, because if this is equal to G0, then it means that G1, G0 must be inside the G0. Yeah, sorry. So G1, G0 must be inside of A. Right? No, so I'm not sure. Why is it empty? Now I'm confused.
No, not empty. That's the only.
No, what was it?
idea is G1.
Is G1.
But
No.
so A.
No, it's not right. No.
A is not assumed to be an ideal. Right?
No, it's not an ideal. It's
a
submodule.
submodule of G1.
Yes.
So this is a true condition also. What is?
The point was that the only
Ideal.
such G0 submodule is G1 because of 3.
Now I'm a bit confused because G1 we saw in the case of G0 symbol that it splits in two parts.
But none of them satisfy that G1, comma A is contained
Right.
in A.
Right, in fact. Okay, so it somehow is an empty condition. So whenever you have this condition, it implies that A is G1. So it's an irreducible condition about this. Okay, now I have it better. So it's not that G1 is irreducible.
No, it's that.
No.
The only module actually is satisfying that is actually G1.
Yes, the only module doing this thing is G1. Okay. So this is this one is equivalence as this condition. Only module is A equal G1 with this condition. This is in a simple algebra. And maybe, as we see in the case, if we see in the case of the of SLMN, it will not satisfy this condition, the module.
Yes, so maybe another way of putting it is condition 1 says that if G1, comma G1A is contained in A,
Then A is equal to 1. Yes, it's better.
yes, yes.
So it's not that no one will satisfy, but it's better this. Okay. I would prefer not to go to this irreducibility question because I wanted, you remember that we studied the example, so we studied the example of the case of G equal to SL MN. Remember this case? So in this case we had this decomposition. I'm doing it because we need it in a moment. So the G0 was the sum of SLM plus SLM over a field C, say over C. And then G1 was the tensor product of the, so this part is G0, and this part is G1. So it is SLM, no, it is, how do we call it? We call it CM times Cn star, meaning the dual representation, so it is this, and then plus, so it was decomposing into two parts, Cn times Cn star. And now there was the question that Mousson claims the irreducibility of this module under the action of SLM and SLN, right? But I did not work it out. I promised I was going to work out, but I did not. Okay, it's a sad thing. But you remember there was at some point an issue of the tensor product decomposition, but one is to be careful because this is not like a G module tensor, a G module. It's like this is SLM and this is SLN module. So this tensor is, you know, it's not, because you make a question of like a decomposition of tensor product into sum of irreducible representation, but this is not this case, right?
Yes.
So it is a different case. No.
Can you explain why G1 is equal to this?
No, we did the last time, Nicola, is because. So what is the question?
Why G1 is equal?
As a vector space, it should be clear because this, you remember, if you have a vector space V tensor a vector space W, this is the matrices. This is the endomorph, no, not the endomorphism, the morphism between V and W, right? So it will be this matrix in coordinates. And then this matrix plus this. So as vector space, there is this equality. Now we're making also a claim that okay, we know that it's a G0 module, but the claim is that this is irreducible and this is also irreducible. The question is raised by Fabrizio is like, if you have so this is a G module and this is a G0 module. When you take a tensor product, it decomposes. It's not irreducible in general, it decomposes. Here is different. In fact, Mousson doesn't use tensor product, he uses this thing. Because,
it's only vector spaces, right? That's the It's only his vector spaces, right? Not
yes,
representation.
he writes this little square to mean that as module is not action of the same thing here and here, but here you have the action of SLM, and here you have the action of the other law here.
Yes.
You remember?
Of the product. It's representation of the product.
Of the product. So it has a different characteristic.
Yeah, and it's always reducible.
It is always?
Yes.
There is a theorem saying it, because I think we see it by hands in this case, a special
I
case.
think for groups.
Okay.
Sure, but I think also for the reality.
No, but in this
Actually,
case,
all the reducibles of a product are of this shape. The
What is the question?
The reducibles of a product.
of a product of what?
Of the atoms, in this case SLM plus SLM of a direct sum. There are all tensor products of the irreducible.
Yes. What you say makes sense, but yeah, one should sit down and work it out. But when I looked at it, I had a few minutes to look at, and it looked to me it's not tensorable. This different thing. This is why it is irreducible, not. maybe by hands also in this case. I'm sorry, I did not work better on this. Now, I wanted to give, so more or less, I don't want to go into the calculation, but what you prove directly this is a faithful G0 module. And you prove directly this fact is easy. You check that when you do bracket G0, G1, you get all G. This is really easy. The only condition here is to try to find the G0 submodule of G1. But here, if these are irreducible, you have only two candidates to check this. And then you check that this condition is not verified for neither of them. You see what I mean? So you should verify for every G0 submodule of G1 this condition. So you have two possible, this one and this one. But none of them satisfy this first one. Marta is not happy. Oh, you're so only asleep. She's like,
I was just,
no, after lunch I know it's not possible.
Provided the two irreducibles are not.
Yes, but they're not isomorphic,
Yes.
because I think it's because one is the contragradient of the other, right? I mean, contragradient, so this much I found. The contragradient representations are isomorphic if only if there is an invariant bilinear form. But here I don't see the invariant bilinear form. So I mean, I know I should have done this, but next week will be even worse. I could not prepare. So this is all exercise. Apart from this fact that Fabrizio points out that is to be checked. Now, I want to say what is an invariant bilinear form on G, but this is very clear what it is. So we can have bilinear form on the Lie superalgebra G, and well, you know what is bilinear form, and we can have it a symmetric bilinear form, what is called the supersymmetric. So of course it respects parity always. Supersymmetric bilinear form says that when you do xy, this is equal to -1, the parity of x, the parity of y, and then yx. This, let me check, because I want to say more, but I want to be sure. Ok, sì. Right. I don't have the definition. No, it is the same. But then I want to, if I'm looking at KMN, this space, CMN, if you can think about K equals C. You know that symmetric bilinear form is associated with a matrix, right? And I want to say what are the standard. It's great because in the book I use different notation than here. I cannot believe. I want to use Katz notation, but okay, in the book I use the other one. Yes, then I have to use this. So, disaster. I have two possibilities. Right. No, I have various possibilities. Matrix associated. So it is clear how this form should look like, because it will be a symmetric bilinear form. That is a scalar product on the even part. While on the odd part, it will have the property that reverses the sign. Okay, so it will be an antilinear skew product. So what is the matrix that we associate? We associate the matrix I call B that has this aspect. So it will be as follows. So in the lower, it will be we need to take one of this with the minus sign. So we put the identity here and minus the identity here. It's a convention because we could do the other way, put minus and plus. And of course, this is, I mean, we're taking the standard, but there are many that are conjugated that, I mean, obviously. So 0, 0, then here put the 0. And then I think that, I forgot, I want this to be consistent, that the product of odd with even is 0. I forgot. So, consistent. We use the word consistent to mean that the product of x, y is 0 for x even and y odd. This is an extra condition. And then, on the upper, we want a scalar product. Here we distinguish even and odd case, as typical for the algebras. So we do this. We put 1 here, and then here, this one, and then we put identity here, and identity here. The 1 is there only if it has odd dimension. Okay. So, let's see an example. In the case of Cm, for example, C2m, 0. So what I want is this is the identity and the identity. This is the one. Lorenzo is not happy. It's a scalar product. What is the scalar product? You have to take a vector, take a row vector, the matrix, and column vector.
Why did you write this matrix and not the diagonal?
You answer to me. Why? Steve, don't speak. It's very important. It's a key point of Lie algebra course. I cannot believe who was your teacher. This incompetent that did not point out the importance of choosing that instead of the usual. No, it was my student.
You try to ask to Riccardo, he knows the answer.
No, but
He's taking my class.
you did not do this yet, did you? Did you do this yet?
Yes.
Ah, you have done. Ah, so Riccardo. Why? Scalar product. Why? Because it's so convenient to put identity in this position. Why don't we follow Lorenzo and put the identity here? What are these algebras thinking about? All crazy people. It's a shame. This professor teaching this class is not explaining things properly. I cannot believe.
I mean, that's the same basis, just in different order.
Yes.
Yes.
Certainly it is a matter of taste, in fact, to choose one or the
It's not
other.
the same basis.
No.
It's not the same basis.
What do you mean, same basis? No, it's
It's not the same basis in different order if you choose the
No, no.
It's really different.
So
No,
it's
it's
not
the-
standard scalar product on C2m.
well, eventually it is isomorphic.
On an even vector space, all your products are isomorphic. So you're
Yes.
free to choose whichever one.
Yes, he's right. So you remember it's the same, if you have a non-degenerate symmetric bilinear form, you can always reduce it to the identity over the complex field, right? So really it's a matter of a choice of basis, whether to use the one that is the identity or the other one. The problem with the other
I choose
one...
yet another one in my class.
Using another one. No, this is the one used. Did you? No.
This one,
No, you
one
put the
choice
one
is
here.
much better because if you put one on the anti-diagonal, you don't have to distinguish between even and odd rank. And everything
Anti-diagonal.
Yes.
Ah, that one I did not see.
that works.
The problem is that when you study the Lie algebra, and we will do it in a moment, root spaces, if you choose the diagonal one is fine, except the root space will come with the imaginary. So the root space will we can work it out. But if you, so it will come not so nice, the root spaces.
No, the problem is that you don't have diagonal matrices in it.
Yeah, you don't have the, yeah, it is a consequence. The Cartan will become 2 by 2, the diagonal 2 by 2, right? The cosine sine is this one. No, the Cartan matrix is not the diagonal one. Which is
It's not
this,
there are no
it
diagonals
is
at all.
this, yeah, no, it is this, it's cosine, sine is this, right? So it's the root space decomposition that raises the problem. We will see. The skew diagonal. Who does the skew diagonal, Fabrizio? Who does it? The books all do this. The skew diagonal, the other diagonal that you suggest.
I don't know where I took it. I just tried it and then it works.
Ah, you try. Ah, I would never
And
try
you can
it.
treat the three types B, C, D at the same time
Ah.
in using the anti-diagonal. It's much nicer.
Mm.
So also, yes, and for the symplectic, you also put the 1 or minus on the anti-diagonal.
Ah,
It's nicer.
let's follow what is here.
Yes, yes.
Okay, so we give a, so what we're doing now, because we discussed the SLM n, which is one type of simple algebra. Now we're going to another type of algebra. So it is the same thing for Lie algebras. For Lie algebras, you remember you have this the SLN, and then you have the orthogonal SON. And then you have the symplectic, right? The families. These are the families of Lie algebras. Ricardo looks at me puzzled. See, is the incompetent professor. No, you did this, right?
Yes.
Okay. Now we did the SLMN is this, similar to this. Now we're going to do these other two. Now, how is defined in the classical case, how you define the special orthogonal? So this is the Lie algebra that whose matrices behave in a certain way with respect to a standard form defined on CM, the orthogonal. So we do the same. So we define. So we give the definition. So we define OSP Mn as the set of matrices X in GLMN. So it will be a subset of this with the condition that when we, so is X transpose B plus Bx. So this is the condition. Hopefully, let me check because I make a disaster with the sign. I hope I got this. There is no sign here, hopefully. There is no sign. Right. This, now, and you can work it out. Really, you can take a matrix in, I mean, it is really a silly calculation. Let me explain. So you have to take a matrix, say, of this type, I don't know, UVPQ transpose, and then you apply this B. You put, what is it? Let's give a name. So we call this block, we call it G, say, and this block we call it H. So we do plus So you have to do this calculation. It's, I don't know, I mean, I don't want to do it because I already did it once in my life, but the point is that this will impose conditions on this matrix S, on U, V, P, and Q. I don't know, do you see how to do this? Clearly, you already know what conditions should be on U and on Q, right? Because if these two are 0, you see, this means an observation. So if V and P are 0, this will read as U transpose G plus G U equals 0, and the other reads should read the other way, right? So it should read Q transpose H plus H Q equals 0. So this will tell you that U is orthogonal and Q is symplectic, because this is the symplectic form. This that gives you what is it? This one is the symplectic I and minus I. So this tells me immediately before I made the calculation that the even part of Mn 0 is the orthogonal plus the symplectic. So, this I know. Then one does the calculation and see what is the rest. I can write this just for the fun, but sì, siamo abusivi. Sì, vado via. Sì, proprio devo andare via. Intanto mi ha già chiamato qualcun altro. Eri tu! Avevo già messo silenzio.
Very short lecture.
No, we try to go to another place.